they don't really have like, it's not like they have big like sidewalk style. But it wasn't even the sidewalk chalk, because the sidewalk chalk was almost too light, and so it was like this special type that Gale had that's like super high quality. I remember when I was TAing for Mark Snapper, he was talking about how expensive like his chalk that he had for his classes was just so expensive. I don't even know the brand, but it's like super high quality. Yeah, but this, we'll see. I think I'm gonna use the blue today. So anyway, I know you guys are probably fried now from being done with that exam. So today, what I'm going to discuss, and the next week we're going to discuss as well, is sort of biomimetic processes, right? And so the sort of idea of what inspires you to potentially spend the time and effort to carry out a total synthesis can really probably come in many different forms, right? And so, we discussed a little bit about Corey's work, and certainly Corey, I'm going to talk about biomimetic synthesis, and certainly he's had his hands in a lot of areas, and biomimetic syntheses, specifically some of the work that I'm going to talk about today, he contributed to, but I'm not actually going to talk about his work per se. I'm going to focus more on William S. Johnson and some of the work of Stork and Eschenmoser. But sort of, I would say that by and large, what sort of, if I had to guess, I can't really speak for him, but when you read Corey's work, you sort of assume that the driving force behind that in many ways is often, let's tackle this molecule, let's make it the most efficient way we possibly can. And if that requires the development of new synthetic techniques and methods, then so much the better, right? Developing chemistry within total synthesis. And that's sort of counter to what we'll talk about maybe in a few weeks, which is when you have a new method and then try to highlight that in a total synthesis and use that method. It's sort of like it's just coming from a different perspective. Develop the synthesis, and I use that as an inspiration to develop new chemistry, or develop new chemistry and then use that as an inspiration to sort of show it and prove it within total synthesis. And so, sort of related to what we discussed last week. But one of the things that one of my real favorite sort of inspirations and driving forces is sort of using nature-inspired syntheses, right? So how does nature make these? They're natural products. They didn't just come from God, right? There was some way that they were actually created that came from likely simpler precursors. And so if you can sort of think about how those simpler precursors were there, perhaps that can provide a template for you to devise your synthesis. That can certainly help you develop new chemical methods in a way, right? If it's something that nature's done but we can't really do, and certainly there's a lot that nature can do that we can't do, but at least it would provide inspiration to develop those new techniques. And so this sort of idea of biomimetic synthesis was actually first coined by Robert Robinson, and sort of the example that I put up on the board here is perhaps the first biomimetic synthesis that was described, and this is sort of synthesis of tropinone. So I put this up here. I assumed that some of you guys would get done a little bit early and get a chance to look through this, but in the sake of time, what I'll probably do is we'll go over this sort of synthesis together. And so looking back at this, really what Robinson sort of saw was that perhaps this molecule would come from a double monic, okay? And then what we'll see, there'll be a sort of a decarboxylation step. And so you guys remember the monic, right? The monic is an enolate sort of addition into an imine, right? And so sort of idea here is when you look at this molecule here, right, you have this sort of, when you lose water to this, what you're really left with is a dialdehyde or bisaldehyde, okay? And then you have your amine, right? And so what's going to happen here is the amine is going to condense on the system, right? You have your H2N, Me, that's going to condense on the one side. Right, and then 1, 2, 3, 4, 5. What's going to happen here now is, I'll sort of draw it a little bit more. Steady, but really what's happening, again, water is going to add it, but formally that's going to be protonated. And then likewise over here would likely be from a hydronium or something like that, right? But really what you're doing is you're exchanging out this oxygen formally with the nitrogen. Okay, and so what you are at is right, and really what this is it's on either side it's a dehydration from an aminium, right? So either way that you go with this, you can lose water one way. It's symmetric, so it really doesn't matter. But again, you can protonate. I'll sort of leave out that protonation step. You're going to protonate, eliminate water. Right, you'll be at your aminium. Okay, and then what you have here is this sort of dicarboxy acetone compound up here. Again, the tautomeric form of that, if you sort of draw it out, right, you'll have a very high tautomeric preference for something that will look like this. Right, again, it's sort of beta, beta keto, or in this case, yeah, I mean, it's a beta keto carboxylate, right? So either way that you're going to sort of draw this, you effectively have your monic, right? So what's going to happen here is you're going to add in once. We can go ahead and lose water over here as well, so maybe we can just sort of draw this in a single step over to this side. Again, it's not going to be, I'm just sort of conserving board space and trying to get through this quick. You can clearly see it's going to add in, it's going to go to the nitrogen, right? And then the nitrogen is going to kick out another equivalent of water, so you'll have this guy over here. And again, you'll have the exact same thing will happen on this side now, where you're going to add in. And then what's going to happen, right, is now you're at this. Blue was working well. Okay, so what you're going to be at is okay, and then this is simply just a decarboxylation on both sides, right? So you're going to decarboxylate one way, right, on the carbonyl, the methanolate will protonate, and then you'll decarboxylate the other way. And what you'll get to is trophanone. And again, the overall yield in this Robinson process was fairly low. It was only 17% yield. But again, if you sort of think about the level of complexity of the molecules that people were generating in those days, this was a very significant discovery. And it's subsequently, this overall process and this idea has been optimized up to like, what do I have, 90% yield. So again, it was sort of a proof of principle that here's this proposal for how this might be made. We'll try to actually mix these things together, coax it to do this rearrangement. Perhaps we'll learn some chemistry during that process. And more so from a sort of academic standpoint, we're sort of giving, in a way, we're providing support that perhaps this is the way that the molecule is made biosynthetically, right? So again, Rick last week brought up the sort of idea of how enzymes do certain things, and so we're going to be talking about reactions today. Certainly many of these processes that are biomimetic are indeed driven by enzymes, right? And so these enzymes have evolved over time to do these reactions very efficiently. So it's not to say that we're trying to necessarily trump biological processes, but it's more, I would say, that we are inspired by potential biological processes to be able to do them in the absence of an enzyme or in the absence of biological type systems and settings, and try to do them in the lab. And so it's not necessarily saying better than biology or anything like that. It's just actually, in fact, being inspired by biology to develop chemistry and develop our sort of understanding of this process. Step around is horrible, huh? All right, back to red, I guess. Okay, so anyway, so this was 1917. Again, significant discovery. Again, Robinson coined the term biomimetic within the synthesis of tropinone, so this is widely regarded as the first biomimetic synthesis, or at least a synthesis that is inspired by at least a prediction or a hypothesis of how the molecule could be made in the literature. And so, you see a lot, and if we have time, I'll discuss one of the guys who's like one of my favorite practitioners of developing biomimetic synthesis, and that's John Porco of Boston University. But what I'm going to talk about today is two of probably the most famous examples of biomimetic syntheses, which is this week we're going to discuss sort of steroid cascade processes, so polyene cyclizations. And then next week we'll talk a little bit about antiandric acid cascades, which will sort of reinforce Woodward-Hoffman rules and get us thinking about Woodward-Hoffman rules in terms of fairly elegant cascades. And then again, if we have time, next week we'll discuss some more current examples of this. Okay, and so in terms of steroid cascades, again, like any molecule, right, like any synthesis, the most powerful and the most important thing to do, right, you see this a little bit when we were talking about Corey's retrosynthetic analysis, really it's going to be the carbon framework that you have to sort of focus on. That's going to be the most important thing, right, is build the carbon framework. And this is one of the reasons why some of those powerful reactions that are out there are some of these reactions like a Diels-Alder, where you're making multiple carbon-carbon bonds simultaneously, right? And so when you can make many, many, many carbon-carbon bonds simultaneously through cascade processes, it really opens up the possibility for very powerful processes. And so just to give you an example of what I mean when I'm saying a steroid cascade, just to show you a sort of a generic or just a representative example of a steroid. This is going to be damarandine, which is actually synthesized by Corey. And I actually had this synthesis of this molecule on Hume a few years back. Okay, so the sort of idea behind this. Okay, so this is meridine, I guess you would call it. So anyways, this is an example of a steroid. It's just one that I think you can sort of see the steroid cascade fairly readily in, because when you start to look at this process, what it really comes from is we talked about terpenes a little bit the other day when it was brought up how some of these natural products, or the longifoline was made. Steroids are in essence kind of like terpenes, right? They come from squalene, they come from several terpene units, a specific terpene unit, and that's squalene. Okay? So I'm going to go ahead and draw squalene in a very suggestive manner. Okay, so this is squalene. This is what virtually every steroid actually comes from. Okay, and if I start to actually, you start to sort of look at the bond disconnections, right? You can start to see, right, how when we sort of go through this process, you can start to see this sort of six-membered ring, six-membered ring, six-membered ring, 1, 2, 3, 4, 5-membered ring process. You guys see that? So in general, how this could form, at least in principle, right, would be through some type of squalene cyclase, right, where an enzyme would come, this sort of squalene would form itself inside this enzyme. That enzyme might force it into a specific conformation, and then maybe it might protonate at this position and really set off sort of a cascade process whereby you would zip up this ring system, right? And so again, you look at this molecule and you can sort of see that a lot would be taking place throughout this cationic cascade process, right? This molecule doesn't have any stereogenic centers, right? This molecule has 1, 2, 3, 4, 5, 6, 7 stereogenic centers. So in a single step, right, an enzyme is going to take this linear system and perhaps convert it and generate 7 stereogenic centers simultaneously. We're also generating 1, 2, 3, 4 carbon-carbon bonds simultaneously. And so again, this sort of idea of this process, right, that perhaps steroids would come through this cascade, you could clearly see would be a very appealing process for a synthetic chemist who's trying to develop molecular complexity. So this is sort of a theme behind here. Okay, and so in the sort of mid-60s or so forth, people began to try to think about, here's this idea of how steroids might be made. Could we potentially understand this chemistry and develop similar processes ourselves? And so some of the early work in this area was actually done by Stork and Eschenmoser. And I'll show you a sort of very simplified version of this, again, because there's a lot of chemistry that has to be understood before being able to sort of run and carry out this sort of one-pot demeran diol synthesis, right? We have to sort of understand a little bit more of the intricacies behind it, okay? And so, again, part of this comes down to this stereochemistry involved, and the Stork-Eschenmoser hypothesis has to do with the net stereochemical outcome that might take place through these. And so we can sort of draw these out and see them, but what I'm going to show you guys is that if you take so here's instead of a sort of polyene, we've got a triene here. Okay, and what I want you to pay attention to specifically is that alkene there, because that's going to be the one that's going to be different, okay? And so that would be a Z alkene, okay? And what we're going to see is that there's going to be a difference between when that's Z and that's going to be important in these syntheses, okay? And so the idea is that if you have this alkene at this position in the Z, okay, what's going to happen is if you have that in the Z, turns out that there is a concerted process where all of these will take place simultaneously, but it's going to adopt process here. Okay, so what's going to happen is you want to try to adopt in all of these. What you're trying to do is you're trying to get those alkenes to arrange in a way where you're going to get a sort of a chair-chair conformation. Okay, and so how that chair-chair conformation is able to adopt itself is going to effectively be how we are going to get our stereochemistry. And so the chair that I'm talking about here is, I had a different color. So this is 1, 2, 3, 4, 5, 6, and so you guys can see the chair there, right? So that's 1, 2, 3, 4, 5, 6. So that's a chair, okay? And then what's going to happen over here, right, is now this is going to be the chair as well. So we're going to make a 6-6 ring system, right? And it's going to go through a rearrangement that's going to be a chair. Okay? And so as this one gets protonated in the presence of, say, an acid, right, this one's going to form this bond here, and this one's going to form that bond there. Okay? Can you guys see that? Okay, so can you see that when this sort of forms, what you have here at the sort of ring juncture, right, is that your proton here and your methyl group up here are going to be on the same face of the molecule. And so the net result of this is that what you're going to get is in fact a cis-declin. Okay, where your CH3 is here, proton is there, and again, the bonds that we're looking at here, right, are going to be this one here, right, and then this one here. So this was sort of where our alkene was. Okay, and so again, the fact that the alkene in that sort of separates the two rings is Z would lead to the cis product. Okay, and so now if we go ahead and we try to do this with the trans alkene, what you find is that you actually get, with the E alkene, what we're going to see is in fact that leads to the the trans declin. Okay, let me just complete this so we're. Right, and then our carbocation is basically there, so if we somehow protonated right, then something might come in and attack that position. Okay, so let's look at the E one. So now we'll look at the E geometry. Okay, so now we're looking at the E alkene. Okay. And again, we're going to go ahead and we're going to try to adopt in the same way we wanted to go through a chair-chair conformation. So we'll go ahead and we'll try to draw this. Again, it's concerted, so it's going to want to go through that chair-chair conformation. So we go ahead and draw it. This will basically be the same, but we're just going to flip this up, right? So this isn't really going to change at all for us here. But what is going to change for us is now this is going to be flipped the other way. Right? So, okay. And so there's that E alkene, right, within there. And now what's going to happen is we're going to effectively make this carbon-carbon bond here, right? So this is going to, so if we protonate here, this is going to attack here, this is going to attack there, right? But again, if we draw that proton in there, right, now what we're going to get to is the trans declin. Very piss poor drawing of trans declin. Right, so if you imagine that getting protonated now, right, and our carbon cation might be over there. So now we get to this sort of trans declin. Okay, so the sort of idea here was that you can have, depending upon when you're doing these Pauline cyclizations, when you sort of get this process to take place, or if you're going to get this process to take place, it's important that you pay attention to what the stereochemistry is at that alkene that's going to inevitably be leading to these. And so this is sort of the idea, at least the hypothesis behind this. Now it turns out that that some work was done along these lines in terms of trying to figure out a way to get this to in fact work. There's a little bit of problems in terms of the certain racemization and so forth, but nevertheless, this sort of principle applies and will be important as we sort of go forward in what we're going to talk about today and what looks like we'll likely move on to tomorrow, which is going to be the synthesis of progesterone. Okay. So again, this is a sort of early work. This is some of the background. It's important to recognize is sort of the power of a potential cascade process in these big forms, and then again, how you might be able to do polyene cyclizations if there's a sort of stereochemical outcome that's going to take place because of, the fact that this is going to be a concerted overall process. Okay, so I'm going to go ahead and erase this, and I'll start talking about progesterone. Again, the focus of this class today is going to be, or this course is sort of synthesis and photosyntheses. Okay, and so markers make you think that they're working, and then a little bit of drawing and they die on you. Okay, so the focus of today's class is going to be progesterone. You notice progesterone will look a little bit different. This is a steroid. Again, it has that 6-6-5 ring structure. Proton up, this proton down. But this is the structure of progesterone. Okay, so progesterone is a sort of hormone. It's involved in obviously the sort of female menstrual cycle, pregnancy, embryogenesis, and so forth. And so it's obviously a very biologically relevant target. And so it became the sort of focus of some of the syntheses that were out there. It's actually important to recognize that this molecule, before the discussion that I'm going to give you guys today, this sort of synthesis had been done previously by Stork, but in fact, even though he had sort of had some of these hypotheses, he made this molecule, in fact, in a slightly different way, where he basically developed one ring at a time rather than trying to make multiple rings simultaneously. And one of the reasons why I think Stork was sort of unable to do this is that oftentimes the cascade, right, you'd have this sort of potential 6-6 ring system, but really it's at this 5-membered ring that's here. And this is sort of, again, we sort of discussed this chair-chair conformation from the Stork Eschenmoser hypothesis, which would entail that you need, right, to have a 6-6 ring system, right? And so if you're starting off your cascade process, say up here, where you have that 5-membered ring of the natural product, you're sort of not going to be able to get there, right? And so William S. Johnson actually, who we're going to discuss about the total synthesis of progesterone, this is where he made his sort of first okay. he made the observation that when you have an alkene in there, you'll get the 6-6 ring system. But if you want that 5-member ring system, but one of the ways you can actually get the 5-6 ring system instead of the 6-6 ring system is to actually set off this process with an alkyne. Right? So you still have that alkene in there, but the problem is that when you have an alkene over here, then it's going to want to adopt the chair-chair, right? And so then you're going to have a 6-6 ring structure. But steroids have that 6-5 ring structure at the top, and so it's really, this is where William S. Johnson sort of made this discovery. And so if you took this molecule, what he found was that if you take this with now an alkyne up there instead of an alkene, and you just treat this with formic acid, 15 minutes at reflux, what you get is an extremely impressive 90% yield of, so you take this and you get a 90% yield this molecule here, right? And so you can start to see that this, in fact, you've got the ketone up there, you've got the methyl group, you've got the proton, you're starting to resemble, right, this top part of the molecule right there. You're able to get that 5-member ring. And so the question is, why is this happening? So again, it's sort of, we know why the 6-6 ring structure would form, but now let's look at the 6-5. And the reason is that if we go ahead and we sort of draw our sort of chair, we start to draw our chair-chair ring structure, right? We have right, so that's going to be our chair on this component of it. You can't, because of the sort of orbital overlap, you can't in fact get the sort of 1, 2, 3, 4, 5, 6. You can't get that sort of 1, 2, 3, 4, 5, 6, right? Because the orbital overlap, you can't start to, like if that was an alkene, now you can start to make it look like a chair. But with the alkyne in there, there's just way too much. The overlap isn't great, right? You'd have to force a lot of ring strain in order to do this. And so instead, what's going to predominate is the sort of 5-endo-dig process. So this is what we're going to start to see. The orbital overlap actually becomes better in the alkyne to form the 5 sort of endo, endo-dig rather than the sort of 6 endo process. Okay, and so again, this is the sort of process through which it's going to go through. That is in turn going to lead to so now we still have that stereochemistry there, so we've got our methyl group up, we've got a proton down. Right, and then the effect we have is that sort of carbocation system there. And again, in the presence of what we're sort of looking at here, right, that's going to now be trapped with the formate. And so that's why that's effectively what you're getting trapped with there is the sort of the formate counterion. Okay, and so again, you can sort of hydrolyze that down, and now you can imagine once you hydrolyze that, you could be at sort of ketone form that you have up here. Okay, and so this was sort of one of the early findings that sort of made this sort of 5-6 ring structure. Now we've started to get something that very closely resembles that 5-6 ring structure, and effectively puts him in a position to try to use this type of cascade in the synthesis of progesterone. Okay. Okay. So what I'm going to do now, so over the next 15 minutes, is what I might do is, with the remainder of the time here, is we'll discuss the retrosynthesis. We'll break it down to sort of a more manageable target, and then maybe what we'll do is next week we'll come in and we'll do a class next week. The following week, forget spring break's coming up at some point, but we'll go through the next week. The point is next week we'll discuss the retrosynthesis today, sort of what he identifies as being his sort of starting material, and then next week we'll do the sort of the forward synthesis. Okay. Okay. So again, here's the key step that's going to be in his process, and so here's just the model. So again, 90% yield, extremely impressive process. Okay, so from a retrosynthetic standpoint, again, what we're going to see here is what he's going to do, okay, is he's going to effectively take this molecule here, okay, this sort of 6-membered ring right here. He's going to sort of pre-make this molecule. It'll make sense as I'm going through it, but he's not going to cyclize up through this whole process. He's going to make it a little bit simpler. He's not going to make all 4 rings at the same time, but what he is going to do is he's going to make a 3rd ring. So he's going to make those 3 bonds simultaneously, okay? And the way that he's going to do this is this 6-membered ring, and I'll discuss this in a moment. You look at this carbocation here, right, and you think about generating a carbocation at that carbon. Okay, and let me ask you guys, do you guys see any issues with trying to generate a carbocation right there? Why might that carbocation not be that stable? All right, if I wanted to have this carbon be a carbocation and set off that cascade, what might be wrong with this carbocation if you try to generate one there?
I think it's one of the non-classical carbocation.
What do you mean by that?
I don't know.
So just thinking simply, like what might be wrong with that carbocation? Do you think that you'd be able to form that carbocation? Well, it could isomerize, but I think the point that I'm trying to make is that would probably be a very difficult carbocation to generate, right? Because you're sort of, it's like trying to generate a carbocation right next to a carbonyl, right? It's going to have destabilizing factors through that carbonyl. This is an alpha-beta unsaturated carbonyl, right? And so if you're going to try to put a carbocation there, right, you've got effectively a resonance form where you can put another carbocation here. So that's got a high destabilizing factor. And so unfortunately, this is a very elegant synthesis, but unfortunately, one of the things that, one of the potential limitations to this approach is going to be that he can't really generate that carbocation in that position. So he uses something slightly different. And he, in fact, makes this compound from a 5-membered ring. And so, again, this isn't to take away from the synthesis, but I think just make a point about one of the limitations of the method, which is I'm going to be just going back and forth between colors because one keeps running out and then the other one keeps getting some of the juice back. Okay, so what he's going to do is, instead of this being the ring, he's going to make this ring from this molecule here. Okay? Now, what are some of the differences between this one and this one is now if we look at this carbocation that would otherwise be formed there, is that going to be more stable or less stable than the one over here? What are the advantages behind this carbocation versus the carbocation that we might have seen over here? It's symmetric, exactly, which is key, right? If you draw the resonance form, you're going to have a resonance form where now you have a carbocation over there, which doesn't matter because you can just rotate it around. So it has that symmetry, which is going to help them to a certain extent. And that's also a stabilizing factor, right? When you start to draw resonance forms of this one, right, through the carbonyl, you're kind of SOL, right? You might draw a resonance form, now you're putting the carbocation adjacent to that carbonyl. In this case, you've got two resonance forms, right, which are symmetric, right? So it doesn't matter which resonance form it goes through, so it's got that advantage. But it's also two resonance forms which are both tertiary carbocations. So the ability to sort of generate this carbocation is sort of much easier. And again, if you sort of think about the conditions that he had used previously to sort of affect the cascade process, they really weren't all that strong. It wasn't like he was using triflic acid to get this to go, right? He was just using formic acid. And so he probably didn't want to have to create conditions which would be harsh throughout this process because it might lead to a lot of side process. He just wants to generate a carbocation and cleanly go through the process. So he's going to make this, and we'll show how he did that specifically next week. But you can probably see how he's going to do that fairly quickly, right? You can imagine if you can sort of cleave that bond, right, through sort of an ozonolysis, and then it's simply an aldol condensation, right? And that's going to lead to that phenone there. Does everybody see that? You just sort of think backwards. Right, so that ozonolysis would lead to that, right? And then this is simply an aldol condensation between there and there. Okay, so it's just a two-step process, but it's still, it's worth noting that the limitations of this, he has to, and that sort of speaks to his own vision in terms of the thinking about the synthesis and how it might be able to be handled. He recognized that, maybe this might not work, but we could use this, and just in a couple steps we can convert it into the product. So it's not a huge limitation, but it certainly speaks to one potential limitation of the polyene cyclization. Again, that's not to take away from the synthesis. It's just always good to sort of think about the limitations of different things. Okay? And now from here, this is where he's going to go to his polyene cyclization process. Okay? And so again, if we sort of start to think about where those bonds are, maybe I'll just draw them in red. Right? It's those bonds that we're going to make. So we're not going to make all 4 rings, but we're going to make 3 of the rings. It's still pretty impressive. It's still very impressive. And what that's going to lead us to is a molecule that's going to look something like where that's our sort of alpha. Okay, so again, in terms of the bond connections, right, we're going to that one, and that one. So those are our ring systems. Okay, so this becomes the new target. Okay, again, because we're going to generate a carbocation there, right? That's going to become our new target. We've dramatically simplified this molecule. We now only have a single stereocenter on this compound altogether. And again, it's now all alkenes, and it's just about trying to put this molecule together. And so anytime you're going to do retrosynthetic analysis, right, which clearly he's probably thinking about now, at this point you may want to dissect this molecule in a way that might simplify it in terms of 2 complex fragments, right? Anytime you want to sort of limit your, when you're sort of thinking about retrosynthetic analysis, you often want to, at a point where you can sort of divert, rather than you want to sort of cut it in the middle, right? You'd rather have 2 medium difficulty targets than 1 really hard target and 1 easy target, if you will, right? Because the total step count. You'd rather spend say 5 steps making one and 6 steps making the other, and then coupling them together rather than take 12 steps to make one and 2 steps to take the other, right? Because your sort of longest linear sequence would be a little bit more difficult. And so when he does this, what he views as a decent connection point, he's not going to start to build up this one, he just wants to sort of cut it in half. And so what he's going to do is he's going to dissect the molecule at that point. And how do we make alkenes? What's one of the ways, the most popular way to make an alkene? Nowadays, maybe metathesis, but at this time, this thing, biomimetic, right? And so again, you could, I'm sure that you thought through this. You could have the aldehyde on one side and the sort of phosphonium on the other. But what he chooses to do. I'm going to put this in brackets. Because it's going to be a quote-unquote this group. Again, you probably don't want to do the Wittig with the alcohol around per se, but it's going to be something like this, maybe a protected version of that or something like that, but at least in terms of retrosynthetic analysis, this portion of the molecule is going to have the phosphonium on it. This other part of the molecule is going to have this part of the molecule. So again, we've simplified it. Particularly this molecule right here has now become very simple looking. I'm sure that you guys could probably come up with a synthesis of that fairly efficiently. So now this part of the molecule here, we'll sort of discuss this a bit. Well, so anyways, the target is something like this. But what he does is he's effectively going to use not necessarily this component to sort of go in with. What he sort of does is he takes a step back, and at this stage, he's actually going to introduce, again, it's just all about strategy. The actual target that he's going to go after is actually slightly different than this. Okay, and again, the sort of idea here is that this would simply require Grignard addition, right? Or methyl lithium or something like that, whatever that sort of methyl-based nucleophile is going to be. And this is a decent place to do this, right, because none of these are sort of electrophilic. You can add in there, and you can sort of get to that compound. So really, I guess I should just draw this one. Maybe just make it easier. What I'll do is I'll just draw this. And this one here. Okay. And again, the chemistry at this point isn't really necessarily the sort of prettiest, but it ends up working. Again, he makes this. He's going to end up making this through an aldol condensation. I'll just show those as protected. Okay, but basically this is going to become his target, and I'll talk about that in terms of the forward way. He'll have him protected the key tau. And then again, this part, as I said, is fairly simple as well. And again, there is a little bit of manipulation that's done up here. Like actually, as I'm sort of looking at the retrosynthetic analysis again, it's not necessarily that target specifically, but I think the point that I'm trying to make here, as we sort of look forward to next week, is that this is going to be the polyene cyclization. It's going to be this key step here. And then what he's going to do is he's going to try to simplify it to sort of bring it forward. And this is something that you see, as we'll go through the synthesis, it's not, the power oftentimes in a biomimetic synthesis is often that the biomimetic step is so powerful and creates so much complexity so quickly that oftentimes you can get away with sort of taking the roundabout way to sort of get into some of these other targets. And we'll sort of get through that again, how he goes through this. This is not really the best part of synthesis, but he's just trying to get there. And so this is effectively where that polygene cyclization is going to get set off. So again, we'll discuss how he made this next week, and we'll discuss how he made this next week, and then the whole sort of forward synthesis to that. And then after that, we will discuss one of my favorite biomimetic syntheses, which is going to be the indiandric acid cascades of Casey Nicolau, which is, I think, really, really impressive and will, again, sort of reinforce your understanding of Woodward-Hoffmann rules and stereochemistry and electrocyclic processes. So, okay, so with that, I guess I'll let you guys head out, and yeah.
What does the brackets mean around those oxygen?
Just some protecting group. So oftentimes, so it's just, if it's formally that. That's kind of what I was trying to do up here, and kind of didn't really do it justice. The point is that this is kind of what he's going to have up here eventually. It's going to be some surrogate for this.
Okay.
You know, protecting groups can come in different forms, right? We often think of PBS or whatever, but sometimes the protecting group can actually be a synthetic precursor that's sort of set up just so that the chemistry will behave itself. Kind of like this kind of almost being a, I guess it wouldn't be protecting group, but it would be a sort of a necessary synthetic equivalent, if you will, to what this is ultimately going to be. All right, so with that, I will let you guys head out.